Awesome, thank you. So today I'll be talking about meteor shower fluxes that we compute using Global Meteor Network data. So to start, why do we even want to monitor meteor showers and their fluxes? So for any space assets during their operational time, the major cause of some sort of meteor impact probability are not meteor showers. They're sporadics. However, on very short time scales to hours and days near the peaks of major meteor showers or outbursts, there can be an elevated chance of kind of a directional way from which meteorites come from. And because they are much higher speed than sporadic meteors, they have higher impact energies. And there's a possibility to minimize the impact probability. Satellites can turn their hard side towards the radiant or minimize their cross-sectional area. And as you know, we recently launched some sensitive and expensive instruments to space. There's the James Webb Space Telescope that has 25 square meters of meteoroid collecting area. So we really do want to make very accurate predictions in the near-Earth environment about the activity of major meteor showers. And what is a constant concern is that we have some unexpected outbursts. The 2012 Draconids, last year Perseid outburst, and we had the Andromedids as well that weren't really predicted anywhere. So we want to make sure that they are well observed and we can make better prediction models based on those observations. The best way from at least our perspective, because this is what we have to work with, is to use the Global Meteor Network data that we have at our disposal. So the network currently has over 700 stations all over the world. And the idea is that we use low-cost video cameras combined with the Raspberry Pis that are running our open source software. Anyone can build it, anyone can install it. The instructions are online. You don't have to buy anything from us. We don't have any financial interest from it. What's great about the data is that we already have 24/7 global monitoring. Calibrated data exists. We produce already orbital data, and we have a real-time data processing pipeline that's in place. And we thought, well, why just not add flux to it and see what we get? So the first thing you have to do when you're computing meteor shower flux is you have to determine if the sky is clear or if the sky is cloudy. And that can be quite difficult because we have cameras in various locations, for example, like perfect skies or heavily light polluted skies. The problem is that sometimes in certain locations, we can't even see the clouds, just the stars disappear. It's just so dark. So we developed an algorithm that goes in, and if it detects any stars, then it determines the limiting magnitude directly on the actual detected stars, and then it predicts exactly how many stars are supposed to be seen in the field of view if the sky is clear. We correct for any obstructions, we correct for vignetting, et cetera, and we also make sure that the moon is never inside the field of view. And after this, you can basically see how the software works. It tries to match up the detected stars versus the predicted catalog stars. And the idea is that if this ratio is above 0.5, which you're going to see in the next plot here, so if it's above 0.5, so this is a ratio between the matched and predicted number of stars. So ideally, it should be around 1 if the sky is clear. And if it's above 0.5, you can actually nicely see that the sky is clear. And we also basically tell it, well, it needs to be clear at least for 1 hour to make it even worthwhile determining the flux there. So how is flux computed? So this is just kind of some basic theory. The flux is simply defined as the number of meteors that cross through a certain area in a certain amount of time to a limiting mass. So there are a few numbers here that are quite easy and we already know. The number of meteors, the number is quite easy. I mean, we already have the number of detections that the detector produces. The observing period, well, that's easy because I explained how that's done. The two difficult numbers are the limiting mass and the effective collecting area. So the way the collecting area is computed is you first take the raw atmospheric collecting area at the meteor height. You literally just project the camera field of view to a height of, I don't know, 100 kilometers, or it really varies with the shower. And then you correct for the sensitivity, vignetting, atmospheric extinction. You correct for meteor range. Meteors further away are fainter, apparently fainter, for the radiant, elevation, and angular velocity correction, and a few other ones. And what happens is that you end up with a reduced area because you're not observing efficiently over the whole area that your camera is seeing. And then taking the estimated apparent meteor limiting magnitude, you use a conversion function to a mass where you estimate, what your mass limit is, or a magnitude limit. It really depends how you want to frame it. We described this algorithm, and it's currently it's actually published in monthly notices, so anyone can find the algorithmic details. And here I'm showing the flux profile of the Geminids. These are 2019 and 2021 combined, and inspired by some previous amazing work on video meteor fluxes, we have decided to combine different cameras together. What we actually do is we just check at the same time. We just combine the number of meteors observed from different cameras and the total collecting area, and then we bin everything together to get much better number statistics and a much more accurate flux. And we produce a plot like this for every single shower, where you can see exactly when the observations happened and what the average radiant elevation was, the radiant distance, and everything goes into flux computation. So that way you can actually say if one point doesn't look good. If one point doesn't look good, you can review it. So we have to verify the method somehow. So we used other observations, previous numbers from the literature, to compare the fluxes for the Perseids, the Geminids, and the Quadrantids. And we can see that our numbers, which is this point here, and this point here, and this point here, actually matches well for most showers. The Geminids are an interesting case. They're about a factor of 2 less than what is expected. However, that would mean that the ZHR of the Geminids, according to these other observations, should be 200. So probably they have some sort of a broken power law distribution, or maybe these other observations, for example, set from like the radar or the lunar impacts, might have some calibration issues. So finally, applying this method, we observed a 2021 Perseid outburst. As you can see, so the normal maximum here reaches an HR of about 120 or so, and the peak in 2021 of the outburst reached almost a ZHR of about 300. One thing to keep in mind is that we still have gaps in our coverage. So as you can see here, this is what I personally call the Pacific gap, because just simply because of the geographical distribution and because there's so much water there, we don't have many cameras. So if this outburst happened over the Pacific, just the number statistic wouldn't be this good. We wouldn't be able to get good fluxes. And of course, where everyone is talking about this conference at the Tau Hercules. So because we put the pipeline into place just before Tau Hercules happened, we were able to get over 1,000 high quality orbits that were published automatically on our website. Within 12 hours of when the outburst happened, we got the flux profile within that time, and we measured a peak ZHR of about 25, but because the shower is so low velocity, it might be really hard to convert nicely between the flux and the ZHR, as someone previously mentioned. And because we didn't have really good coverage in this area, we actually missed the first maximum that some people have observed. And that's it. So thanks to all the hundreds of people who are involved in the network for their hard work.